Hi, thanks to coming to our session. So I'm Taka from MIT Media Lab, currently working at the University Tokyo. Here I will present to you our new interactive system that we call inDepth, which enables force-based interaction with objects beyond the physical barrier. In this presentation, I talk about the physical barrier, which used to be an obstacle, but now with our system becomes a new interface. Physical transparent barriers are common in everyday scenarios, like in aquariums or museums, that separates between content and people. While these barriers have important roles, it prevents us from reaching into the 3D spatial contents on the other side. Such barriers are also common for 3D volumetric displays that makes it hard to point at the specific 3D spatial XYZ coordinates beyond the barriers for the input interaction. We can point these contents in 2D but can't point in depth with 3D depth coordination. So our research question is, how can we give people access to reach and point at the spatial contents beyond physical barrier? The key idea is that transforming the physical barrier itself into a force-based touch interface. With inDepth system, by directly touching the barrier surface, people can freely manipulate the cursor to any 3D positions at a depth just by applying a force on the barriers with your fingers. Only by putting several force sensors beneath the physical barrier, users can build their own inDepth systems. So we utilize the physical barrier and transform it to an interface. As another instance, in a bakery shop with the inDepth system, you can imagine, the customers can select their desired items just by applying force on the glass of the showcase. Customers can press lightly on the glass to select items at the front, but they can also increase the force intensity to select items deeper in the back. And here is the design schematics of the inDepth systems. There's a 3 components: the physical barrier, object inside it, and force sensors. The great advantage in this configuration is the surface and the items kept unmodified. What you need is just deploying force sensors beneath the barrier. It's just that. These sensors translate force direction and intensity into a position in the 3D space. This system also translates the input force signals into various predetermined functions. For the hardware implementation, we are using a 6DOF force sensor. Specifically, we are using the Scale force sensor toolkit that was published at WIS19 due to their ease of use. You can see each black module underneath the object detects 3DOF force signals in real time. But together, they form a network of sensors that enables interaction on rigid objects. For more detail, please see that work as well. Also, please note that our method is applicable to other types of force sensing systems. For instance, the inTact system published in CHS16, which uses a single 6DOF industrial sensor, could also work for inDepth system. For the software implementation, we carefully designed the mathematical algorithms as well. Since human perception is not directly proportional to the amount of physical stimulus, it is not a good strategy to directly convert the input force intensity to the depth information. Therefore, we have developed a new conversion algorithm based on Weber-Fechner's law, where the depth is logarithmically proportional to the input force. Currently, the parameters are empirically determined, but they could be determined in more systematic way by future user study. For the applications, we consider that the inDepth could cover many different application domains. To understand this broad application space coherently, we have categorized various possible scenarios into 3 domains. First type is volume imagery, which has transparent barrier and 3D graphics as a content. Second type is clear showcase type, which also have transparent barriers and physical items inside. As stated, museums and aquariums could be classified into this category as well. The other type is the geometric content, which contains an occluding surface with graphics content. To see structures inside a gadget, like a screwdriver, inDepth could provide an intuitive manipulation. So this is a demonstration in the educational setting in astronomy class. The viewpoint and the depth of graphics is controlled by applying force with your fingers. For this kind of volumetric display, applying rotational force onto the surface can be directly translated as a rotation of the graphical contents. The 3D coordinates of the physical world and the rendered protein model are aligned so that people can intuitively interact with the rendered content. Also, in another medical scenario, the pressure applied with your palm can control a planar cursor, which is useful for seeing the cut intersection of the rendered human skull. By pressing differently, you can intuitively control the tilt and depth of the intersections as well. So there are many research opportunities based on this new interaction method, and now we are planning to extend our application scenarios. As mentioned before, it could be a really fascinating field for real-world deployment in aquariums or museums. Also, we recently found that inDepth system has gained new opportunities in the world with COVID-19. Now we have many transparent barriers in our life, like at a reception in a shop. These barriers can be transformed into new interfaces by attaching just small force sensors. Okay, this is the end of the pre-recorded session. Let's move on to our live session. Thank you for watching. See you soon.